Hello, everyone. Just a few seconds here. I will just upload my slides. How are you guys doing? Excellent. It's good. It's almost, we're almost there. So I hope everybody's doing fine. Can you just tell me if you can see the screen, please? Okay, perfect. Okay, so I hope for the people at least attending the lecture, they are kind of, they are being caught with, all the fluid flow kind of principle that we discussed over the last few lectures. We spend more time on this chapter than what is designed for this course, but as I mentioned many times before, that those principles are a key point for all engineers. They are working for different applications, and you will see yourself that is required to do some analysis somehow related to fluid flow in a very specific system. And the minimum that you have to understand and know how to do is how to really design a system carrying fluid from point 1 to point 2, and making sure that you, when you design the system, you consider all the losses you have in the system, and then apply some principle in order to find out what is needed in order to move these fluids in these systems. So this chapter today is going to jump into chapter 11. This is going to be the last chapter that we will have problems on. The last two chapters was mainly more of an information for yourself. You can expand later on, but chapter 11 will be the last chapter that we have an exercise problem where we have to really do some analysis in the problem analysis sessions. So we'll try to finish chapter 11. So in next week and the week after, basically going to finish the tutorial on chapter 11. Chapter 6 and 7 will only basically presenting the theory, and for people are interested to expand their knowledge, they can later on work on that. So today's chapter is a continuation of chapter 6, which is we learn how fluid is moving in the system, and we know that we apply a simple principle Bernoulli equation to describe energy in the system and calculate some losses in terms of either fractional losses or eddy losses. And looking at different configuration of the piping, is the pipe is connected in series or parallel, we kind of did all these analysis. So at the end of the day, you need to drive the flow in these systems. Okay, two type of fluids that as we would discuss in the beginning of this course is fluid or gas and liquid. So if we are dealing with gases, in this case, we need to look at, for example, compressors that is used to drive fluids, or if we are dealing with a power generation, so we look at the gas turbines for this case in order to generate power out of flow going around these equipment. Versus if we are talking about liquids, now we're going to talk about something called pumps, and these pumps are a device that is moving fluid. The main function of this pump is basically moving the fluid in the system. So in this chapter today, we're going to talk about pumps and turbomachinery in general. And as I mentioned, that some of these principles might need much more work to really fully understand the whole subject. And sorry to keep saying this, but this chapter or this kind of topic can be by itself a course, a whole course. So I have taught before like courses only in turbomachinery. So you can imagine that what we are just presenting in this lecture is an introduction to these kind of principles. So and which is fine at this stage of the fluid mechanics course. So we're going to talk about some basic principles and some basic elementary engineering estimate for the performance of these fluid machines, and just talk briefly about this pump machinery that is the minimum knowledge for engineer they need to know. Okay, so turbo machine is many applications for that. As I mentioned, it's either you are generating energy by flowing the flow around this machine or these turbine blades, okay, or you are kind of providing the mechanical motion in order to drive the fluid. So we call like in this case either a pump or compressor versus turbines. And this turbine could be hydraulic turbine or gas turbines. So you can see here, for example, in this application here, the turbo machine that we are talking about here is something like this. So this is for power generation or propulsion application. So they're looking at the for example, the rocket engine or the turbo engine used for aeroplanes. You will need some air to be flying into in the exhaust to provide the thrust. If you remember our chapter 3 for the momentum change. So in this case, you need to provide a huge amount of velocity and mass going out. So in order to do this, you are forcing the air to come into a combustion chamber. So the fluid will come from, here. So the fluid will come from outside, going through a compressor, okay, going to the combustion chamber. You are adding the fuel in order to produce this amount of energy for much more pressure built inside the system, and then the fluid will go outside here by very, very high velocity compared to the the inlet velocity. So we have V inlet here, and we have V outlet here. And this V outlet here will be, much higher than what is V inlet in order to provide the momentum change that is required for, pushing all these, all these device or the airplane forward. So so we use many terminologies for that. So we are either talking about like the compressor here is a turbo machines that we are dealing with. And in this case, we need to find out how the fluid is flowing over these turbo machines. So this is one of the application. And there are some, some courses and textbooks only talking about the turbo machines and turbines flow analysis. This is another picture just to give you an idea about like the size of these turbines. So this is, a gas turbine for power generation applications. So you can see here the blades of the compressor size versus like, the human size can be varied with different sizes. So the fluid going inside these machines is one of the, aspect on fluid mechanics that we need to understand in this course. Applications also including pumps, and the pumps basically is basically a flow mover, like it is a device used to move fluid in the system. How pumps are used to drive the fluid in the system is just like basically converting the mechanical motion inside these pumps to a flow energy. Okay, if you remember what is a flow energy, anyone remember what is a flow energy? Is from all what we discussed, flow energy is, anyone? You guys remember? What is the flow energy? What is the relation for flow energy? That's it? Q? No? Missing one thing? Okay, guys, like, please try to remember this. We've been talking about this many, many times. Okay, flow energy is the pressure times Q, right? Volume, flow, right? So if it's a rate, it's going to be power. So if you're talking about the pressure times the flow rate, will be a power required to move the fluid. So which means that most of these devices are needed in order to provide this flow energy, which means that it is basically providing flow rates at a certain pressure. So as simple as that, okay? Pumps are using, we are using term pumps when we are dealing with liquids. We are using term compressors when we are dealing with gases, okay? And both are the same kind of things. The turbine, the turbo machinery or the rotating machinery, or these rotating equipments include also the wind turbines. And the wind turbines here is the opposite. You have this flow energy, the wind energy, and this wind energy will be basically hitting those turbine blades in order to make the rotation for the mechanical motion and then convert it to electricity later on. So turbo machines or or rotating equipment can be either creating this flow energy or using the flow energy to convert it to the mechanical energy. Okay. So the purpose of this course is basically, or the purpose of, this chapter here is talking about how we can, do some basic engineering estimates for the performance of this machine, power requirements. This is the least you have to know in your fluid mechanics course, right? So many people are doing design in their senior design projects, and they keep forgetting about when they are dealing with fluid in a system, you keep forgetting completely about what they have studied in the fluid mechanics course. So you kind of, putting, piping between two elements where the flow is, going without really calculating pressure drop, pressure losses, doing some analysis for the fluid. The most important thing about the analysis as an engineer is being able to provide an accurate solution, or better solution, or optimum solutions, right? This is what is different between you as an engineer and the technician, that we can fix something without really a full understanding of the whole idea of the operation. Okay, so you are expected as an engineer to do analysis, and those analysis can be covering different elements of your design. One could be material related, another one will be dynamics related, but also maybe thermal and heat transfer related, and also another which is a fluid mechanics or a fluid analysis in your system, in addition to control analysis and so on, right? So when you are basically working with a very complex system in engineering discipline, you have to keep in mind that any part of that you are optimizing in the design, they will end up with a better design. Okay, so the difference between a good engineer and an engineer that is just doing his job without even understanding what he's doing is the level of analysis that you're going to do. The more analysis you will take into account, the more depths of detail that you are kind of including in your design, the better the design is. And this is leading to the first step of innovation, the first step of really creating a good idea, the first step of creating a new design. The first step is providing an efficient solution for a problem, or a best solution for the problem. All these are related. Okay. As I mentioned, we don't have that much luxury in this course to really provide all detailed analysis of the fluid around the turbine blades, and this can be by itself is a whole course. Okay. I have a textbook on pump machinery in theory and practice. You are welcome to browse this book later on when you finish your course, if you are looking for connecting theory to practical applications, how the engineer are dealing with this turbine and pump machinery in many engineering systems. So I just put this for your reference here if you are interested to browse this textbook. So again, let's start with a pump, because this is the easiest one. Dealing with an incompressible fluid always is much easier dealing with gases. And this is where we're gonna focusing on these chapters. So we're gonna talk about pumps. Okay, so pump is basically converting mechanical energy to hydraulic energy. Okay, and this hydraulic energy will be later on can be considered as a flow energy, because this hydraulic energy here we're talking about pressure, But pressure here is not only the thing that we needed. We need this pressure to move flow rate that is that much. So, so the pump is basically providing hydraulic power or generating hydraulic power from the mechanical power that is provided to this pump. And what is driving the pump? We call it like, the prime mover of this pump, which is basically electric motor or any type of motors. Could be like, diesel motor or something like that. It's just like a device that is creating this mechanical rotational motion and for the pump to operate, okay? So the purpose of hydraulic pump is to supply the fluid flow required by the hydraulic system. And as I mentioned, this is very important to understand those principles. So one of the very tricky understanding for pressure is not generated by the pump. Pressure is generated by the resistance, okay? So imagine if you are pushing, like, okay, if you are, standing at the front of one of your friend and try to push your friend, right, in a certain direction, right? If this body or your friend is resisting this motion, you start feeling the pressure, start feeling the force that you are kind of acting on. But if your friend actually keep moving with your, pushing it in the certain direction, and then you are not really resisting your push, you don't build any pressure. So which means, you can look at the fluid flow in system like same way. The pump is providing the ability to create pressure in order to move fluid, okay? So that's why, the resistance in the system on the piping system is what create the pressure, okay? So if you have no resistance, that means you have no pressure. If you get a pump and the exit of the pump is open to atmosphere, you are not going to see any pressure build up outside, okay? So all the time, think about, you have a resistance in the system, and this resistance is, pushing back the fluid from moving, right? So the pump is a device that is able to build up a certain energy, and this energy is a flow energy, is in terms of pressure. So this pressure will be built up based on the resistance that you are creating in the system. Okay? This is very important into your understanding about fluid flow in this system. And this resistance we'll study in chapter 6, that this resistance could be because of the friction in the piping, because of the eddy losses in the piping. So all the total energy losses, this considered to be a resistance. Okay, so the pump is a device that is basically to overcome this resistance in this system. Okay. So the pump provides flow, it transmits the forces of this flow. This is kind of more formal explanation of what I just mentioned a few seconds ago. It's this force that you are creating on the flow. It's kind of in order to overcome this resistance in the direction of the fluid flow. Pump also is a device that is adding energy to the fluid. So you're gonna have flow coming into the pump and flow going out of the pump. And according to the conservation of mass, so whatever coming in has to be the same as whatever the flow coming out. Okay, it's easy to do this for the for an incompressible fluid, because in this case the density is the same, assuming that the pressure is not changing that much, the density. So in this case, the volume flow rate coming in equal to the volume flow rate going out. But in general, for any systems, for any pump system or a compressor system, mass flow rate coming in equal to mass flow rate going out. Okay, and the pump, what is the pump is doing is by moving these plates or moving this part of the pump. We're gonna look at specific design in a few seconds here. But this pump is creating some vacuum pressure in order to suck the fluid from the suction side or from one side of the pump and push it on the other side of the pump. Okay, that's why we're gonna talk about some two type of pumps. One pump called the positive displacement pumps, and the other pump called the rotodynamics pump or the dynamics non-positive displacement pump. Okay, positive displacement pump, in the term positive mean here that it's going to be always flow rate going out. And if you close the valve at the exit of the pump, you might either you break the motor or you kind of you damage the system, right? So in this case, positive displacement pump is talking about, fluid that has always positive motion in the delivery side or the exit of this pump. Okay, the application of the positive displacement pump is when you have a need for a very high pressure application, like all hydraulic systems or hydraulic circuit used for cranes and lifting very heavy loads and stuff like that. We are always use positive displacement pump. Okay, rotodynamics pump or the dynamics non-positive displacement pump is relatively is used for lower pressure requirements. I mean, like relatively lower, right? But again, it can vary for a wide range of pressure and flow rates. But in this case, and as I'm going to explain in the in the slide later on, the dynamic positive displacement pump, sometimes you can even have a build-up pressure inside without really delivering the fluid outside. So it kind of resists or withstand a blockage in the exit part of the system. Okay. So many applications, as I mentioned, for positive displacement pump. This is just a sample of these type of pumps, including a plunger pump here, a gear pump, right? All these pumps, screw pump or helical pump, vane pump, right? Loop pump, right? Many hundreds of type of these, type of pumps. And it is based on this motion, the mechanical motion that you are adding into the pump, right? And creating, fluid flow in the system. So you're creating these volume flow rates with the pressure that you are pushing. So you can imagine here for a plunger pump or a piston pump here, as this piston going up, fluid is sucked from this side. And now the valve here, or this check valve here, is closed while the piston is going down. So this will be closed and then this will be open. So the, as the piston goes down, it is just pushing the fluid here to the exit. So we can have this valve here and this valve here is operating. One will open on the suction and one will be open at the delivery. Okay. So in this case, if you are dealing with liquids, right, you are taking fluid by moving this piston up from these sides. Okay. And now when you are going down, this valve is closed, and then this valve is open for the fluid to go outside here. So in this case, when you are pushing down, what happened here for these fluids? This fluid has to go out. Why? Because if we are dealing with liquids, you remember when we talk about the bulk modulus of elasticity in chapter 1? The fluid cannot be compressed. The liquid cannot be compressed, right? You are pushing the liquids, the volume cannot decrease. It's not similar to the gas, right? So the liquid has to be pushed in this direction. And that's why we call this is actually a positive displacement pump. That once you are pushing the liquid or the fluid, the incompressible fluid out, it has to go out, okay? Because in this case, either you are building pressure inside the pump that can, exceed the maximum allowable pressure for this equipment and you have damage, or the motor itself that is driving this motion will not be able to, push more force, which means basically it will burn out, right? That's why, most of these applications are needed for very high pressure, okay? And the mechanical pump here could be by reciprocating motion, like the plunger system, like in point A, or it could be a rotational motion, like in the gear pump, like this. So the fluid here will be carried between the gear teeth here, right? So, and goes outside here. So as more as this fluid, the fluid will go like this and then go like that. As long as this gear is rotating, liquid is carried between the teeth of this gear, and then goes outside. So as long as this gear is rotating, liquid are going in the delivery, in the exit side here, right? So if you are blocking this system from exit, pressure will be built up, and then either you break the system or the motor will be burned out. Okay, similar, different configuration here. It's just the operation is. Or the mechanical design is different, but it's all the same thing. Mechanical motion, pushing the fluid out to overcome the resistance downstream of this pump. So if you have resistance in the system, this pump is basically pushing the fluid in order to overcome these resistance. I encourage everybody here to look at many YouTubes that is showing the operation of these different type of pumps. Okay. As I mentioned here, many devices, for example, here, this kind of, a piston cylinder device. So as this crank is rotating, I hope you have taken some of these in your dynamics or mechanics course. So you can actually create like linear motion of this piston by connecting rods and the crankshaft. So as long as this is keep rotating, the piston will go up and down, or like, left and right, in order to make like the suction effect and the delivery effect. Okay. The only problem for the reciprocating piston that, as long as this piston is moving, the connecting rod here, right, is like this one here, okay, is like, applying different type of force depending on the angle of this connecting rod. So you might see variation of the fluids and also the pressure. Okay, so depend on the angle of this crank, how this is rotating. Like for example, in this side here, so as the more this connecting rod here, let me just do that with red here. This connecting rod here is rotating. Okay, so every point on this connecting rod will have a velocity that is, if you can see here, for a certain angle d theta, this will be, the velocity will be like, omega r d theta, right? If you take the component of this velocity in this direction and in this direction, you can say this omega r, this is angular velocity, r d theta sine theta, right? So this kind of connecting rod here, it's a rigid body motion. So once you are moving, this body here in this direction, all elements will be moving. So this also will be moving with omega r d theta sine theta, which means that this piston is moving with a certain velocity depend on the angular position of this crank, which means that if the piston is pushing fluid, but every time the velocity changing, that means the flow rate going out is changing, right? Which means that we are expecting for a positive displacement pump, like a piston pump, to have a, kinematics. It is, yeah. So this is basically, suggesting that the flow rate is variable with the angular rotation. So if you have like the flow rate is variable, also the pressure will be variable because the forces also will be variable. So the only problem with this piston displacement pump is the variation of the flow rate with the angular position of this crank and the pressure as well, right? That's why sometimes designs like this is a multiple piston cylinder device. You can have a plate or a disc that has multiple pistons. So one of these pistons will be making a suction while the other is making delivery, while the other is in between, right? So overall for the pump, you might kind of, make this variation of the flow rate become less, right? So you can have a less variation, right? I'm sorry, I'm moving fast here because that's not kind of, the depths of analysis that we are kind of trying to cover here. But as an engineer, you will be able to make a self-judgment about understanding the concept of operation of these. So I trust that you can actually do this discovery by yourself if you are kind of came along a problem where you have to deal with pump. What I need to make sure that you understand, it's the fluid mechanics concept behind these these type of application. But every single application requires lots of analysis and basically spending more time for design and understanding the operation of these pumps. Okay. In general, we need to find out what will be the flow rates required out of this pump, what is the pressure or the power required in order to drive these fluids. Just like, a simple understanding of when we integrate a pump in a system, what will be the power of this pump? What will be like the efficiency, the mechanical efficiency of this pump, if we have a certain type of losses and so on, right? So I encourage you to read more about this. So performance of the pump, as I mentioned, it is volume flow rate, right? And a certain delivery of a volumetric output of this pump, right? So it's all depend on, like, how much leakage you have between, these compartments. For example, here, if this piston is moving here and some clearance, you might, build up pressure here, right? That creates some leakage on the other side, okay? So which means that sometimes we call, the performance in terms of delivery of the flow rates, is affected by the leakage, the internal leakage of the pump. And now we have to consider some new terminology called volumetric efficiency. So the volumetric efficiency is basically what the pump is delivering actually, divided by the theoretical flow rates that you are kind of, based on the simple design of this pump. So if you know the amount of leakage, if you know that 3% leakage, internal leakage inside the pump, that means the volumetric efficiency is 97%. Okay. So displaced volume mean, you see here, this is the volume that you are displacing here. What will be the volume displaced here? Can you tell me? For example, here, if this piston has a diameter D, the stroke is L. Okay. So, and imagine this is rotating N here. This is RPM. Okay. What is the displaced volume here? So for each single rotation, okay, what is the volume displaced inside? I'm sorry, it's on this direction here. So this is a suction, and this is a delivery. So we're talking about if this piston here now, and now going up and down. So this is a point, the maximum point where the piston are, and this is the minimum point where the piston are. So how much displaced volume here? Anyone? For one rotation. How much displaced volume? The area, right? The area of this piston times the stroke, right? So we're assuming that this, over time, the velocity is almost the same, right? So if you consider this kind of a steady state motion, the displaced volume without time here is pi over 4 d squared. This is the area of the piston times the stroke, right? So this is a stroke, and this is piston. Okay, what will be the design or the displaced volume flow rate? For number of n RPM. So if you assume constant velocity of the piston, what will be the volume flow rate? Q or Q naught? I think we just say it Q here in the flow mechanics. Yeah, Q here is what? Anyone? The number of rotation, right? So it's basically like, you know, this pi over 4 d squared times L times N, right? And if this N is, you know, revolution per minute, that means this will be the volume, you know, will be meter cube per minute, right? So if you're just, if you are considering this N here per minute, so it's going to be a flow rate per minute, or if you consider it per second, so you're going to get the volume flow rate per second. So it's simple, simple analysis like this. At least this is what you minimum knowledge has to be, right? Okay. Different advantage of this positive displacement pump is high pressure, because this is like, you know, these devices are needed for pushing liquid outside. So those pumps are basically considered for very high pressure at 12,000 psi. That's a very, very high pressure. Okay, most of these pumps are small and compact size. They have very high volumetric efficiency, which means that internal leakage because of the clearance between the moving part of the pump are very small, right? It's only a small little clearance between these pumps. So volumetric efficiency is very high, okay? Talking here about like, you know, above 95%. Small changes in the efficiency over the design ranges. So most of these pumps are, you know, operating at very, you know, constant approximately efficiency for all ranges of operation. And it has great flexibility for performance. Like, you know, for example, if you can rotate the motor by different speeds, you're getting high flow rates, right? And you know for sure that this is a flow rate going outside because it's a positive displacement. There is no any accumulation or any internal rotation of this fluid inside, okay? Reciprocating pump has also this advantage, right? Because if you remember, reciprocating has, you know, for example, selecting the pump to operate, you know, we have to, the variation of this fluid that is going out of the pump with time, because the velocity of the piston is not constant, right? So this variation will affect the performance of the pump. But, you know, this is one of the characteristics. So if you are dealing with multi-piston, like as I, you know, show you here, so this one here is reducing these fluctuations, okay? If you are dealing with gears, actually is, you know, the variation here is very small, right? Because the fluid in between the teeth here, right, is delivered here, and then the fluid at the back of the second two teeth, and then the fluid here, right? So there is some pulses of the, you know, the fluid going between the teeth of the gear, right? But still variation, but the variation here is much more small compared to a piston going up and down. Okay, so we have to be also careful when designing this system, because as I mentioned, this system is, you know, if you have a complete shutdown of the delivery side of the pump, you have to really protect this system by a safety valve that has to open when the pressure exceeded a certain limit, because this pump, if while it's operating, fluid has to move out, okay? That's why when you are looking at the performance curve of this pump, you will see the pump head here is the pressure. So if you have a pump like this, okay, this is in, this is out. If you measure the pressure here, this is a B suction. If you measure the pressure here, this is a B delivery. Right? What the pump is doing is increasing the pressure from here to here based on the resistance here, right? So, oops. I don't know what's happening. Okay. So pump head is B delivery minus B suction. This kind of difference between this. So this pressure here, okay, and the flow rate of the pump, okay, can be related together by what we call it the performance curve. So this is basically the pump head, and this is a flow rate, okay? You can see here the flow rate is almost the same. This is all at same rotational speed, okay? So if you have a certain rotational speed, the volume flow rate is constant, okay? But the pressure can be different value depend on the resistance in the system. The more resistant, the more the pump is pushing, right? So in this case, you know, the pressure will increase, okay? And that's why you see it's almost a vertical line here. Ideally, this line can go all the way, like straight line, right? But what happens if you have a very high pressure, very, very high pressure, now you start seeing, you know, leakage in between here, right? In between the pistons, which means that the higher the pressure is, the internal leakage will happen. Now the actual flow rate going out of the pump will be decreased a little bit. That's why when we are presenting this performance curve, we say this is ideal. And now this is a real one here. And this is basically slippage or leakage. Okay. And the flow rate here will be less, right? Because the leakage, internal leakage will decrease the flow rate. But the vertical line is showing that the pressure is, you know, wide range of pressure depend on the system maximum pressure is, okay? Volumetric efficiency, as I mentioned, it depends on how much leakage you have in the system, right? So Q, which is delivered on the system, divided by the displaced volume or the displaced, flow rates. The displaced flow rate, you calculate it from the equation. This is kind of a design conditions. But the Q, the actual Q, is the actual Q coming out of the pump. So the volumetric efficiency, which is related to internal leakage, it is a ratio between the actual flow rate divided by the displaced volume. Okay. So capacity of this volume flow rate in the suction sides, and the displaced volume here is deliver in the delivery side of the pump, right, per unit time. Okay? And the difference between this one here is a slip or the leakage. And here again, this is internal leakage. Writing very quickly. Internal leakage. Okay, so this is not a leakage coming out to the environment. This is a leakage inside internally in the pump from the suction side to the delivery side. Okay, so this is what leakage mean here in this case. Okay, same thing here. You can say that this is eta volumetric here is Q over the displaced volume, right? Or this is like, you know, this Q minus display, okay. Sorry. The displaced volume minus the leakage. Divided by the displaced volume, this will give you 1, you know, so this is 1 minus S over D, right? Same thing here. This is what I think this is what explained what I was talking about here. So this is a Q, the Q leakage here is, you can put like this is the actual flow rates. And this is a total flow rate, which is, you know, the actual flow rate plus amount of leakage. You can look at it at, you know, from this aspect, or you can say, you know, displaced minus leakage over the actual volume. Both are the same. Okay. Another type of efficiency, which is very important efficiency, is called hydraulic efficiency. And this hydraulic efficiency is, we're talking about resistance here, right? So the resistance is coming because of the, you know, the resistance in the system because of friction on other things, right? So the pump will basically, you know, produce a certain head, but this head, part of it is consumed by the friction between all the parts inside the pump. So if you are considering an efficiency that is hydraulic efficiency, it is the same thing here. It's 1 minus, this is the friction losses or the friction head. And this is basically our pump head. 1 minus HF or the percentage friction losses with respect to the pump will give you what we call it hydraulic efficiency. Okay, so this is a hydraulic efficiency. Okay, so if I say, for example, 2% is friction in the head, that means the hydraulic efficiency is 98%. Okay. Another very important efficiency is mechanical efficiency, because as I mentioned, the pump is driven by a motor, right? So this is suction, and this is delivery, right? And this is basically the motor driving the pump. Okay. So the motor is basically putting a power, just adding mechanical energy. So this is mechanical energy, or let's say, sorry, mechanical power. Okay, so you are adding this mechanical power in the pump in order to make this flow energy, right? Or the power of the pump, right? So the mechanical efficiency is same thing. You are adding what we call it, this is what we call it brake horsepower, brake horsepower. And the term brake here is on the shaft itself, like the shaft that is rotating. This is, we call it the brake position here, or the brake, power added to the shaft itself in order to rotate the mechanical component inside this pump. If we measure the power at this shaft, we call it the brake horsepower, the actual power on the shaft itself. Not the power required in order to drive the motor, because this motor is connected to electricity, for example. So this electrical power coming out of the motor, but the motor itself had a certain efficiency, right? So the power is reduced because of the efficiency of the motor. Now the mechanical actual power on the shaft itself, we call it the brake horsepower. Now the ratio between what power losses due to the mechanical friction inside the pump and bearing and backing of inside this machine, if this friction is like 5%, for example, of the total power that you are supplying, that means the mechanical efficiency is 95%. Okay, and this brake horsepower is converted in a way to power of this is like angular speeds times the torque, right? So the torque here is what is pushing these shaft to rotate. This is what is creating. So it's force and radius of this shaft. So the torque, and this torque is rotating this shaft by a certain angular speed. So that means angular speed times torque will give you the power, which is the brake horsepower. These terminology are the basic fundamental terminology that you need to know about pumps. Okay, so those are the basic stuff that we have to keep in mind for the pump. Overall efficiency of the pump is basically a multiplication of all these three efficiency: the volumetric efficiency times the hydraulic efficiency times the mechanical efficiency. So if you have a volumetric efficiency of 0.97, and you have a hydraulic efficiency of 0.9, and then you have a mechanical efficiency of 0.8, you multiply all these three together in order to get the overall efficiency of the pump. As if you have a brake horsepower coming into the pump, Some of this power will be lost because of the friction. It's affecting the, the mechanical motion. Some of them are affecting, like, the hydraulic losses, because of, like, internal leakage and so on. And then some of them are related to, because power is flow rate and pressure. So now the volume flow rate is reduced because of the leakage. So that's why you multiply by the volumetric the volumetric efficiency. The three efficiencies together will give you the overall efficiency, right? Or if you look at it as, what is the output? This is the output from the pump. The output from the pump is a flow energy, right? Pressure times the flow rate. What is the input to the pump? Is a brake horsepower on the shaft. So only for the pump, not for the motor. Like, the motor is another unit connected to the pump. So if we are talking about the pump itself, what is coming into the pump is a mechanical, brake power, which is rotating this, right? So brake horsepower coming into the shaft. What is coming out of the pump as an energy, or a energy per unit time, which is power. Now, when we call it hydraulic power, is the pressure times the flow rate of the, this is missing here, right? So this is Q here, right? Because this is, the pressure is rho GH. If I know the density and G, so instead of, like, and this is the head of the pump, or pump head. So pump head, to convert it to the pressure, multiply by rho G, right? And this Q is missing here, sorry. Input power is a brake horsepower, okay? So let's look at this problem here, okay? So you have a piston, displacement has like 5-inch diameter, 2-inch stroke, right? This is the diameter. Stroke is L, right? So G is 5 inches, L is 2 inches, and operate at 750 RPM. So N 750 RPM with volumetric efficiency. So eta volumetric is 0.92. Okay. What is, okay, first is asking what is a delivery. It's a delivery. Delivery mean here volume flow rates. So A required here, volume flow rates. Okay, what is the Q of the pump? Okay, so how much is that? If the pump deliver an oil of this very specific condition, so I know this is an oil 10W, so I can go to the fluid property table and find out the density of this oil. So I need to find out, against a head of 50 feet, right? So B, so if pump head is 50 feet, and driving this, driving this fluid of 10W oil at 20 degrees C, what is the horsepower required? So the horse power required, right? The power input, okay, in horsepower, if overall efficiency is 0.84. Okay, that's a very simple problem. Just try to apply simple, some of these equations that we just discussed together. So let's go step by step, right? Okay, so now I have a volumetric efficiency and I have dimensions. So this dimension here can basically provide what we call it the displaced volume. If you remember, the displaced volume that we look for a piston cylinder device. Okay. So what is the displaced volume here? Same thing as you, I think we already did kind of solve these in the slide of the pistons. And okay, displaced volume here is area times L, right? So it's pi over D, pi over 4 times D squared. This is the area times the stroke, right? So this will give you the displaced volume. I can just keep everything here in inches. So pi over 4, the D here is 5 inches square times 2. This will give me 39.3 inch cube. I can convert this into gallon if I divide it by 231, right? You can convert everything into SI unit if you want, but it looks like he wanted everything in the British unit for this specific example given in the textbook, and you needed the horsepower at so if I go all the way with the British system, I'm fine. If not, you can do the SI unit and then convert at the end if you want the horsepower. But if I 39.3, if I divide it by 231, I will have this in gallon, right? What is Q theoretical? What does mean Q theoretical? Mean there is a rotational, there's a certain 750 of these, in 1 minute, right? So I can get the theoretical flow rate based on the displaced volume, right? So this is basically the the 39.3 divided by 231 in gallon, right? If I multiply this by 750, that means I can get this number 127.59 gallon per minute. Okay, so this is a total theoretical flow rate, right? So this pump actually has a certain volumetric efficiency. That means, there are some internal leakage here, so which means that the volumetric efficiency, sometimes I keep changing here, right? So volumetric or V is the same thing, right? Eta V, it's eta volumetric, same thing, right? It is basically what Q actual over Q theoretical, right? Therefore, Q actual is Q theoretical times eta volumetric, right? So Q theoretical here is 127.59 times the volumetric efficiency is 0.92. That means this Q actual is 117.4 gallon per minute. Okay. So now if I know what is the overall efficiency, I have these Qs, this is the first, this is A. Right? The second one here, if I know that the head of the pump is 50, overall efficiency is 84, right? I need to find out the input power. So I know that overall efficiency, same thing, overall is output in the pump is a hydraulic power. So this hydraulic power is rho G H of the pump times the Q of the pump, right? And now this is a Q actual, right? Divided by the brake horsepower, right? Or let me just do this. brake power, right? It depends on if I put all the units that can, fit the British system, whatever the power coming out of this equation will be the horsepower in this case, or like feet per pound per second, and then I can convert this into a horsepower by dividing over 550, right? So now rho of this, this is SAE 10W, I guess. Yeah, 10W oil. So I can go to the table and find out this property. So 1.69, this is your density. G here, this is a British unit, so 32.2 times the pump here in feet. The head of the pump is given as 50 feet, right? Times the Q actual here is gallon per minute, but gallon per minute is not the basic unit in the British system. The British system is using feet cube per second, so I have to convert the 117.4 divided by 449 in order to convert these into feet cube per second, right? So this will give you everything in feet and seconds, right? And pounds in the density here, right? And the overall efficiency here, this is a brake power. This will equal to 84. This is given, so I can find out the brake power here. So we can just do this. So the number I have here is 846 feet pound per second. So this is a basic British unit. If I need to find out brake horsepower, all right, I can convert it by 550. This will give me 1.54 horsepower. Okay. Unfortunately, it is still in the markets. Not all the equipment are rated by the basic SI unit or the basic British system. That's why there is a need for all these conversion parts, because you go and buy a pump by the rating of kilowatt or horsepower, right? So you have to make sure that you at least know the conversion between these two. So every time you are dealing with equipment like this, you have to make sure that you can do that. Which is a question, is it possible to go back? Yeah, sure. The question itself, or this one? Yeah, okay. So any questions so far? I wanted, yeah, I wanted to make sure that you, at least for this chapter here, you're getting to know first the minimum requirement informations about the pump, right? Those are the minimum requirement information. Understanding what is volumetric efficiency is, mechanical efficiency is, overall efficiency is, power input versus power output. This is the stuff that we have to, we have to consider. What is a pump head, right? And these kind of things. Okay. Any questions, guys? Any questions? No questions? Okay. So the other type of pump is called centrifugal pump. And the centrifugal pump is, the principle of operation is completely different. Here's not a mechanical motion or a mechanical element that is pushing this liquid in a certain direction, right? This pump are basically, it has a rotor inside. We call it the impeller, okay? And this impeller is driven by motor. So you have a motor here, okay? So I'm looking into from this direction here. So I'm looking here. So what happened here is the fluid is coming into at the center of the pump here, right? Why is that? Because these blades, of course, is going to be lots of design analysis for this. What is the angle of the flow over this blade, and right? So you can spend some time looking at the coming in, flow, vector diagram, and going out, and inside this casing. But in general, here, the impeller is creating, in the middle is creating some kind of vacuum effect, like, reducing the pressure inside this. When you are kind of rotating like the liquid inside the cup of tea, cup of coffee, right? When you are rotating, you remember, the flow in the center will go down, the flow at the outer will go up. So this is basically based on the centrifugal forces that you are creating. So you can look at the centrifugal pump is doing this, right? So the pump is having this impeller rotating, creating suction in the middle, and creating, like, forces on the outer, outer part of this impeller. Okay, this impeller has a space between the casing. So this is a casing here. Okay, so this is a casing here, right? So this fluid is pushed outside to the casing. And why it's pushed? That means the pressure will basically, because now the fluid is hit the casing. So what happened here? All the energy of this kind of very high speed fluid is all of a sudden, like, stopped by this casing. That means, the pressure increase. So the kinetic energy decrease. So the pressure energy is increased, right? So if some part of the casing is open, right, and this is basically what happened here. This was what's happened here. So the fluid will go outside of this pump, right? So carrying all this energy, right? The flow energy, which is in this case will be a pressure and Q, like the flow rate and the Q. So now what happened in this type of pump when it's rotating, and you have, for example, here you have a valve here, and this valve is completely closed. Should slide the total efficiency here? Yes, yes, on. Sorry, I forgot seeing this one here. Yeah, so okay. So what happened if this valve is totally closed? What will happen here? Anyone? Remember, for the piston is pushing all the fluid. The clearance is very tight, so the liquid has to move out. That's why we call it positive displacement. Okay, but for a centrifugal pump like this, imagine I have a valve at the delivery side, and this valve is completely closed. What will happen? Boom? No boom. No, it's not gonna boom. No more pressure will be created, right, Mohammed? I guess that's the right thing to say. Like, it's going to be some mechanical rotor rotating inside, right? Basically build up pressure to a certain point, and that's it. And it's going to be slipping, like, because it's already internal leakage here, right? So the fluid is kind of maintained inside this casing, right? And that's why we don't call the centrifugal pump is a positive displacement. Okay, this is a rotodynamic pump. So we have this kind of thing, and that's why when you are looking at the performance curve of this pump, it has a maximum pressure. Okay, so now the centrifugal pump has is a free passage for fluid hydrodynamic machine between inlet and outlets. So there's going to be some connection. There's a line between the inlet and outlet, the suction, right? So it's kind of fluid is trapped inside the space, right? All machine has a rotating element called the runner or impeller or rotor, and this is rotate freely in the fluids. The transfer of energy between the rotor and the fluid is a continuous, and as a result of the rate change of the angular momentum. So remember the chapter, I think 3. When we have this, momentum transfer of the fluid, when you have these rotational aspects, so we are changing the mechanical motion here into an angular momentum increase of these fluids by pushing the fluid on the outer side because of the centrifugal force that you can basically create this motion of these fluids. Okay. As I mentioned, we are not really getting into the detail of this, but the design of the impeller, you have to really know how the fluid coming inside the impeller, and where is the impeller blades, and every blade of this impeller. So the propeller inside, it has these plates. So the fluid will come here. Sorry. The fluid will come here and go out here, right? So you can actually look at the velocity coming in and V out here in a vector form and do the analysis as it passing through the impeller blade. So each one of these is an impeller blade. And so on. So you can actually study this, and you can also design these blades. What is the curvature of this blade and so on, in order to improve the efficiency of this pump, right? So whole industry, like the whole industry is about pump, right? So one of the equipment only in many applications. So pump is massive. It's kind of considered to be the heart of the industry, because basically you want to move fluids, you want to move like sewage water in the system just outside, right? You want to move the whole fluid, the fresh water in cities or between water distribution system. All this is just like a pump that is driving this, right? So you can imagine the design itself, it's kind of involve a lots of analysis for what is the best design of these pump shapes and so on, right? So I'm expecting you to look at this. So pump design, hundreds of websites and hundreds of textbooks talking about pump design, and different design will basically will be designed in a way. Some of these design actually very flexible design. Even the inlet vanes, you see here, this is the diffuser. The diffuser here is the inlet, creating a change of the velocity vector coming into the pump, right? So if you have a certain change of the flow rates, you might have a flexible design that is creating a different velocity vector coming into the pump. Of course, going out of the pump is based on the design of the impeller itself, okay? That's not really something that we will have time to really spend on, right? But what I want you to know is, when we are talking about the positive displacement pump, this is a discharge, the Q, and this is a pressure, the head of the pump. The relation between these two is a manufacturer chart that is provided by the, whatever the company are designing this pump, right? So for a positive displacement pump, you almost see a approximately vertical line, right? Of course, the reduction here, or the inclination of these from the vertical direction, is based on the amount of leakage here, right? Okay, but in general, for a positive displacement pump is like have a vertical line between this H pump and Q. For a positive displacement pump, this is vertical line. For a hydrodynamic pump, is something like this. This is a curvature. How we determine this curve? It's testing the pump, right? After you design and you actually running the pump, and then you test these pump to find out this, or based on the design model that you build, the CFD model that you are building to create this curve, right? But you can see here is going to be some maximum pressure. This is low viscosity, this is low viscosity, and this is high viscosity, right? Because different fluid will completely, have a different buildup pressure inside, right? But in general, this is a curve of the pump. It goes to a maximum here, right? Even when you close the valve, that means you have a Q is equal 0. You have a maximum pressure that, inside the pump. And this maximum pressure, you can actually design your casing based on it, right? So you don't have any problem with the damage of the pump or so on. That's why you see many applications where they have a valve at the delivery side of a centrifugal pump, and you can even close it completely for the whole shutdown of the system without any issue. But for piston displacement pump, you have to have an auxiliary system. You have to direct the flow. If the pump is operating, you have to direct the flow into a different system, or like, you open a valve in a different direction if the main line is closed, right? Those are the system. I think I'm going to stop here and discuss more the typical manufacturer charts that you're going to find in the in many industry or on the internet. Those are an actual performance curve of the pump. If the pump is using different diameter of this impeller, or if the pump is operating at a different speed. Let's wait for next time. I can explain to you what these charts, because these are actual charts that you're going to see as an engineer or even as a student designing a project. You need to go and find out the right pump for your design. So how are you going to find this? This is what we're going to do next time. Okay. Any questions? Any questions, guys? Any questions? Okay, let me stop the recording and then I will be around for recording here.